Assalamualaikum warahmatullahi wabarakatuh and have a good day. Welcome to our channel. In this video, we will present to you about our integrated design project involving lesson from Principle of Chemical Engineering taught by Dr. Chew Kiam Leng and lesson from Fluid Mechanics taught by Dr. Nur Wahyu Juso. Hope you enjoy this video.
Hi, my name is Muhammad Fitri Syahmi bin Suhaimi.
Hi, my name is Muhammad Fakri Hisham bin Muhammad Fadli.
Hi, my name is Nur Amalina.
Hi, my name is Abdul Syanakuddin bin Abdul Halim.
Hello, my name is Abdullah Nawar.
Before we begin with our presentation, let me give you a brief introduction on what we have done. We have been given this scenario. In recent years, the market demand for acetic acid is increasing because of its wide application. In view of this, our company decides to expand our business chain to produce acetic acid liquid in a new plant. Our team is responsible to develop a plant for producing acetic acid liquid. The developed plant needs to be of low cost and safe to be operated. Therefore, we implemented the knowledge from PCE, Principal Chemical Engineering, and FM Fluid Mechanics to create and design the plant. This is our design project. This PFD, process flow diagram, consists of batch reactor, refrigeration unit, liquid vapor separator, distillation column, valve, pump, and storage tank. If you can see, in yellow color, it is reactive process, and in orange color it is non-reactive process. For reactive process, we are using catalyzed reaction, and all of the conditions will be given by the next presenter. And for non-reactive process, the combination of refrigeration unit and separator are the same as application of condenser. This design is similar as the previous one. This design is used for better understanding and easy calculating for fluid mechanics properties.
Reactive system is occurring in batch reactor. This reaction is a catalyzed reaction at high temperature, which is 200 degrees Celsius and higher pressure, 8 megapascal. At the inlet, 500 mole per hour of methanol is reacted with excess hydrogen gas. Both gases have percent excess of 100%. After reaction takes place in batch reactor, the output are the mixture of 500 mole per hour of acetic acid, 500 mole per hour of water, 500 mole per hour of unreacted carbon dioxide gas, and 500 mole per hour of unreacted hydrogen gas. Therefore, the flow rate of carbon dioxide gas and hydrogen gas in the feed are both 1000 mole per hour respectively. As you can see, this is the chemical equation for the energy balance. It's CH3OH plus CO2 plus H2, and the product is CH3COOH and H2O.
So, the definition of the reactive system is process in which has chemical reaction is occurring. For the mass flow rate, movement of liquid pass through a unit area, dependent on density, velocity of the liquid, which is the formula is M equals to N times MW. For dry basis and wet basis, moisture content is normally expressed as a percentage by weight of either total product, which is wet basis, or dry product, dry basis.
This is for the principle of chemical engineering part, which is non-reactive system. Okay, so this is the simple diagram for non-reactive that we have created before this, and then this is the diagram to show you what we need to find, which is the value of output, which is W, X, Y, and Z. So this is the complete diagram after we calculate the value of the output, which is W, X, Y, and Z. As you can see here, the condition at the input is temperature 200 degrees Celsius, the pressure is 8 megapascal. The gases through the top product and the liquid going to the bottom product, which is the condition at temperature 25 degrees Celsius and pressure decreased to 1 megapascal. For the energy balance calculation, from this equation, we use this step to determine the value of energy balance. As we can see here, we have TBP, which means temperature of boiling point. Means we have to find it at the table B1 from the appendix. Other than that, we use two equations that we use to calculate the final answer of energy balance. Principle of chemical engineering part for non-reactive system. From this project is what we have learned is basically the non-reactive system is no chemical reaction is a core, that the air contaminant emitted by the process are the same as those emitted by the raw material involved in the process, and no reaction by product are produced. The second one, for the mass balance, it is considered for all the material in a process. It also considered as the input, output, and distribution of stream in a process. The mass balance equation simply states that the total mass in any system is always conserved, which is to show all CO2 and H2 go to the top of the product. Other than that, acetic acid and water condense to form a liquid mixture which is going to the bottom product. Furthermore, the third one, for the end energy balance, is considered of the energy input, output, and consumption or generation in a process or stage. In the setup and energy balance, all sources of thermal energy are put on the input side and all items of heat used on the output side. The pressure we assume from our plan is 8 megapascal to 1 megapascal. To find value specific enthalpy, we use table B2 to identify value of Cp to integrate the values. But in this case, for the special case, which is the acetic acid, the value of Cp doesn't exist in the table B2. So that what we do is we just assume value Cp of acetic acid is 0.457 times 10 to the power of negative 3. Lastly, for the calculation of this non-reactive system, we have used of heat of formation formula to find value of energy produced from the non-reactive process.
Alright, for the storage tank design, firstly, we choose the internal floating roof tank design because it uses filters to seal off the tank's wall, which can lower the evaporation and prevent dangerous gas from accumulating. Then, our tank is made of by stainless steel, which can prevent impurity from forming when acetic acid is being stored in it. Then, for our pipe here, we use material commercial steel pipe, which can withstand high pressure and also to prevent energy loss by using diameter 4 inch and schedule 40 pipe, because the higher the diameter, the lower the energy loss. Then we use centrifugal pump because it was designed for liquid which has low viscosity and their flow rates can be adjusted over a wide range. So this pump can increase the pressure for the initial, which is 2 megapascal, and increase to 4 megapascal with max flow rate 250 mole per second to the tank which at higher location, which is 10 meter high. And also we use here gate valve, which is the most common type of valve used in any process plant. It's a linear motion valve that controls when fluid follow begin or stop. Basically, it's totally fully open or totally closed while they are in use. So that's all for our tank design.
In our process unit for fluid mechanics, we have one gate valve, centrifugal pump, storage tank, and we chose our conduit to be a 4-inch schedule 40 commercial steel pipe. The reason why we chose a gate valve is because it's an energy efficient valve option. There is less energy consumed when opening or closing the gate valve in comparison to blow valve. And the reason why we chose centrifugal pump because its energy efficiency, smooth flow, proven reliability, low maintenance, and also centrifugal pumps do not have any leakage because there is no drive seal. In our calculation for total energy loss and work pump, we made some assumptions. Among those assumptions, molar flow rate of acetic acid is to be 350 mol per second, which is equivalent to 21.02 kilogram per second. The length of the pipe is to be 30 meters. The pressure of acetic acid after leaving the distillation column is 2 megapascal, and the pressure of acetic acid after it's being pumped is 4 megapascal. And also we chose our pump efficiency to be 90%. And then from there we calculated the velocity and then Reynolds number, which was over 4,000 turbulent flow, and then we calculated the friction factor and then the total energy loss, and then we used the Bernoulli equation along with some assumptions. For example, the flow is steady, we have constant velocity in compressible fluid, we have delta V is 0 because it's constant throughout the pipe, and work turbine is 0 because there is no turbine used in our process. And from there we calculated the work pump, and then we calculated the actual work pump, and then finally we calculated the power consumed by the pump.
Finally, we have arrived to the conclusion. By applying all the knowledge from PCE, we can determine the exact amount of reactants required at the perfect ratio for the reaction. We can minimize the waste in the plant, yield the maximum quantity of the desired product, and calculate the amount of heat released or absorbed by the system. By applying all the lessons from fluid mechanics, we can predict optimum extensive properties to transfer the fluid into the storage. We can also choose the perfect length, diameter, and material for the pipe to sustain the fluid flow. Calculate work and power of the pump by using the appropriate formula, then forecast the cost of the power consumption in the system. Exact amount, optimum condition, strong material. Then what else? Then we have created the best, low cost, and safe design for our acetic acid production plant.
Thanks for watching.